Most of our planet is water. Most of our cells are water, right? So in order to understand how chemical reactions happen in cells and how kind of life happens, it's important to understand some of the chemical properties of water because that really influences how life happens, right? We're on a water planet, right? So water's all around. Water influences every aspect of life. So let's dive in and talk about how water works. So water, again, is the kind of the platform in which all chemical reactions for living organisms happen. Okay, and water is a really unique molecule because it is a polar molecule. Basically, all that means is that there's slight charges within the water molecule itself, right? So water, H2O, two hydrogens and an oxygen. The hydrogens are slightly positively charged and the oxygen is slightly negatively charged, okay? So this isn't, the overall molecule as a whole is not charged, it has zero charge, but we see slight variations where the oxygen is going to be slightly negative charged and the hydrogen is going to be slightly positive charged. And that gives water some really unique properties because water is polar, water can dissolve many different types of substances. So what's something that can't dissolve in water, right? Like if we try and mix this with water, it doesn't dissolve. Oil, right, or fats, right? So we say something that can't dissolve in water, it's going to be hydrophobic, okay? Hydrophilic means it's water loving and it will easily dissolve in water, right? So water can dissolve anything that is polar or an ionic substance because it can make hydrogen bonds with those molecules. Hydrophobic molecules, though, are typically going to be non-polar molecules, molecules that don't have a charge to them. They're overall, there's no slight negative or positive to that molecule. And those can be things, a lot of times, like we'll see fats, oils, things like that. But hold up, let's talk about hydrogen bonds first before we go any further. So remember we talked about oxygen slightly negative in the water molecule, hydrogen slightly positive? Okay, so when we get a bunch of water molecules together, right, and there's tons of these molecules are so tiny, there are millions and trillions of water molecules and even just like an ounce of water, right? So the hydrogen atom in water is going to be attracted, because it's slightly positive, it's going to be attracted to the negative end of oxygen, okay, the oxygen end of the water molecule. So this is kind of, I kind of like to think this like a weak magnet. It's not the same thing, but that's kind of what it reminds me of. It's not as strong as a covalent bond, but it's enough that the positive hydrogen and the negative oxygen will be attracted to each other, and then maybe something will bump that water molecule away and that bond can break and reform. Okay, so these hydrogen bonds are constantly being formed and reformed in water, but it's that hydrogen bond between water as well as hydrogen bond with other molecules that determines if something can dissolve in water. So what does that look like? So when something dissolves in water, so let's say for instance we take sodium chloride, we dissolve sodium chloride in water, right? That's an ionic molecule, salt, okay? So that when it dissociates in water, it turns into Na plus and Cl minus, okay? So positively charged sodium ion and a negatively charged chlorine ion. Basically what happens is water is going to form hydrogen bonds with these ions, right? So if sodium's positive, the negative oxygens are going to be attracted to that positive sodium, okay, and they're going to make hydrogen bonds with that sodium ion. Same thing over here. Chlorine has a negative charge, and so the positive hydrogen is going to be attracted to that chlorine, and so the water molecules will orient themselves so that way they are kind of attracted to those positive hydrogens and that negative chlorine. Okay, so this happens, this type of hydrogen bonding between the positive regions of one molecule and the negative regions of the water molecule and vice versa. This can happen with ionic molecules are built from ionic bonds, or anything that's polar, right? So anything that can dissolve in water. What have you dissolved in water lately? Maybe some sugar. I just put some creamer in my coffee, right? That can dissolve in water because it has some polar regions to it, okay? So as long as it's polar or ionic, water can dissolve it, and we would call it hydrophilic, okay? As long as it can dissolve in water, we say it's hydrophilic. Water loving is what that means. So water is kind of what we call kind of the universal solvent of life. Okay, so again, all the reactions that are happening in our cells are happening in the presence of water. Okay, And so what does it mean to be a solvent? Basically, a solvent just means that we can dissolve stuff in it to make a solution. Okay, so the solvent of life is water. The solute is whatever gets dissolved. Here we're looking at sodium chloride. We might talk about sugars getting dissolved later. We might talk about maybe proteins being dissolved in water, right? But the solvent is, for most living organisms, going to be water. The solute is whatever gets dissolved to make a solution. Okay, so like I put in a little bit of honey in my tea yesterday, right? So my tea would have been the solvent, and the solute would have been honey. Okay, and that makes the solution of honey tea. And again, because water makes these hydrogen bonds between the different water molecules, that even though they're not super strong, they're strong enough that they hold water molecules together and they keep water from moving too much. Okay, and so that means that water can absorb or release large amount of energy without changing temperature, right? So let's kind of break this down though. What is temperature though? Temperature is really just a measurement of how quickly molecules are moving around, right? So the higher the temperature, the faster molecules are moving. Right? So if we think about like the difference between a glass of cold water and a glass of hot water that you just boiled, the molecules in the cold water are going to be moving much slower than the molecules in the boiling water, right? So it takes a lot of energy to break up those hydrogen bonds between the water molecules in order to get that temperature to increase, right? In order to get those molecules to move around enough so that way the temperature can increase. But why does this matter for living organisms, right? Well, this is really helpful for living organisms because a lot of organisms need to maintain a pretty stable temperature, right? So this ability to absorb or release large amounts of energy without changing temperature helps organisms regulate their internal body temperature, right? It minimizes the amount of energy that they need to expend in order to maintain their body temperature. Water being able to absorb and release large amounts of energy without changing temperature also has a huge effect on climate, right? Typically, well, okay, I don't know, maybe. So if it's like really cold here in like the middle of December, January, like we're like freezing, right? You go to the coast, it's more mild, right? It's not quite, it's still gonna be cold. It's not gonna be like quite as cold. It's not gonna be like absolutely freezing, right, at the coast. So water, being next to a large body of water, helps to regulate the climate to keep it from getting too extreme, either too hot or too cold, usually. Okay, because water can absorb or release that excess energy, that excess heat, basically, that excess thermal energy, and it can absorb it or release it, which helps to moderate the climate. Organisms are also able to use water's heat of evaporation in order to help regulate their systems, right? So evaporation is basically when enough energy is absorbed by water to cause it to change from liquid to gaseous state. And so we call evaporation, right? Liquid to gas. So when water molecules evaporate, like when we sweat and we get water on our skin, when those water molecules evaporate off, that cools us down because when those water molecules evaporate off our skin, they take that energy with them. They take that heat, that thermal energy with them, which results in us feeling overall cooler. Okay, so that's how evaporative cooling works, aka sweating, right? We put water molecules on our skin, they get evaporate off when they get warm enough, and then they take that heat with them. They take that energy with them, which results in us cooling off. Water is one of the unique substances where it is less dense than a solid. So on our planet, we're in a unique kind of like a Goldilocks zone where we have water as a solid, a liquid, and a gas. It exists in all three states naturally in our planet. But water is unique. Unlike most substances in their solid form are going to be more dense than their liquid form. Okay, so water is different though. Water, its solid form, we call ice, is less dense than its liquid form, right? This is why water will float. Sorry, this is why ice will float on in the top of your glass, or like these icebergs floating in this lake right here, right? Or you can get the top of the crust of like a river or a lake will freeze over, but the rest of the lake will be still liquid, right? But why does that happen? So remember those hydrogen bonds? Hydrogen bonds and water being polar is really what's responsible for a lot of these characteristics of water, including water being less dense as a solid. So basically what happens, so when liquid water is all those molecules are moving around, they're making and breaking those hydrogen bonds. They might come closer together, they might get farther apart as they're moving, right? But as the solid forms, as it starts to freeze, those hydrogen bonds start to lock into place and they stabilize at a very specific distance apart. And they're basically stuck in place now as that solid, and they form this crystal structure. And those water molecules are going to be held farther apart in a solid form than they will be as they're moving around in a liquid form. Okay, so that means there are basically fewer molecules of water per volume in solid water than there are in liquid water, which means it's going to be less dense, so therefore it will float on the top of liquid water, okay, which is something that is unique, which means that we can keep an ecosystem running below water, but we can keep an ecosystem running below that ice that's formed, despite the fact that there's a layer of ice there. Water has the unique ability of being what we call cohesive and adhesive. Again, water is polar, so it makes hydrogen bonds. Okay, and so that process of water making hydrogen bonds with itself, we call that cohesion, right? So if you filled up a glass of water and you pour really, really slowly and you can get like that bead of water on the top, like above the rim of the glass, you guys know what I'm talking about? That is possible, water to be like above the rim of the glass because of this property of being cohesive. So it sticks to itself through those hydrogen bonds. Okay, and that also creates the cohesion. That water molecule sticking to itself is what creates surface tension, which some organisms can utilize, right? Like those little water skaters that you see zooming around the surface of water ponds. They can do that because they're so light and their legs are so tiny. They can sit on top of the water like that. Okay, because water is holding on to itself. Water is sticky, basically. And so just like water can make hydrogen bonds with itself, water can also make hydrogen bonds with other molecules, right? We talked about water making hydrogen bonds with other molecules, and that's how they dissolve things, right? That's how water acts as a solvent. But this is water adhesion. Water sticking to other things is why things get wet when they're put in water, right? So why we put our clothes in the washing machine, they come out and they're wet. That's water sticking to our clothes, that's adhesion. This is adhesion is also how water is basically adhesion and cohesion is how water is basically to be pulled up a plant, right? Plants absorb water from their roots, they pull it up through the rest of their bodies, and that's a process of cohesion, water molecules sticking to each other, as well as adhesion, water molecules sticking to the little tubes inside the plant. Water also has this really cool ability to have a range of pH values. Okay, so pH is a measure of how acidic or basic a solution is, which is a measure of how many hydrogen ions, H plus ions, are in that solution. Okay. So for us, we're not going to dive too much into what pH is and how it functions. We just need to know pH can have a huge effect on how chemical reactions proceed and can have a huge impact on how proteins function, right? So like for us, our pH of our blood is right around 7.4, okay? And it stays there pretty stable, right around 7.4. If it gets too high or too low, that can really impact how the chemical reactions in our blood that keep us alive, how those chemical reactions proceed. Okay, but water is one of those unique substances. It has that solvent ability to take on a wide range of pH values, which some organisms like us have a pH value of like 1 to 2 in our stomach, and other places will have a much higher pH value. Okay, so it's just a unique property of water that can take on a range of pH values.